electric motors. You've seen them one way or the other, whether it be in toys, fans, even in phones, but how do they work? That is the exact question we want to answer in today's video. We will uncover how permanent magnets work, tinker with compasses, and use methods like the right-hand rule to make our own simple motor. We'll be doing all this to understand the simple, basic yet fundamental principles of how these engineering marvels, whether it be big or small, are able to convert electrical energy into mechanical energy. So if that sounds fun, tap the like button so we can start right away. First things first, let's develop this simple motor. For that, we're going to need a couple of things. Among those is a magnet, which can either be a square magnet, a bar magnet, or even a horseshoe magnet. You get the point, they come in different shapes and sizes, and if that's not enough, look at this completely different composition of a magnet. The neodymium magnet. This is the strongest magnet in the world, and most of it, about 70% of the world's supply, comes from China. It mainly consists of neodymium itself, but more on that in some future videos. Consider commenting in the comment section the word magnets if you would like us to dive deeper into the world of magnets. That's a lot of magnets. Anyway, the point is neodymium, just call it neo. Well, neo is of different composition than that of the commonly used magnets consisting of a material called ferrite. Hence the name ferrite magnet. So with different composition comes different advantages and disadvantages. This case is no different. With neo pulling weights 10 times its normal weight, it's no wonder they are the strongest magnets in the world. But unlike the rust-resistant ferrite magnets, neo is very prone to rust and must be used in sealed enclosures to promote longevity. These differences are significant, but these magnets have a lot in common. Besides the North and South Pole, all magnets have an invisible magnetic field that surrounds their body, getting stronger and stronger the closer you move to the magnet. It is what gives the magnet its seemingly supernatural power of pulling metals in a distance. And again, if you wish for a deeper dive into how this works, you can comment the word magnets in the comment section. This imaginary field can be seen when moving something like a compass closer to the magnet. Instead of it pointing towards the Earth's North Pole, it points to a different direction. Why is that? This is due to, among other things, the direction of these magnetic field lines, which move from the North Pole of the magnet to the South Pole of the magnet on the outside. This flow makes them move from the South Pole to the North Pole inside the magnet. The second thing we need is a live wire or a complete circuit. We need this because when the same compass is moved next to a live wire, the same thing happens. The compass yet again points in a different direction. This means the same invisible magnetic field found surrounding magnets can also be found surrounding live wires. We can explore this a bit further. Please note that the compass points in a 90-degree angle or a right angle or perpendicular to the wire. Let's have another experiment. Let's take a couple of compasses, arrange them in a circle, and have a wire run through the platform. We'll connect a battery to this wire, having this as our positive terminal and this being our negative terminal. Electricity moves from the positive to negative. So which direction do you think the electricity will flow? Correct if you analyzed it as this direction. Let's plug the wire and analyze the movement of the compass needles. The needles point in a circular similar direction as soon as electricity flows through the wire. What happens when we reverse the electricity flow? All the compasses now point in a different direction, circular and common like the last demo we've just seen. This denotes something. These magnetic field lines move in a circular motion and change direction depending on the flow of electricity. By the indication of this compass, we can also say that these imaginary field lines move anti-clockwise when the electricity flows in this direction and move clockwise when the electricity flows in this direction. Another fun way to determine these directions is using a method used by engineers on a daily basis to find the direction of these field lines in electric motors without the need of compasses. Simple yet effective. Just how engineers like it. No, seriously. It is called the right-hand rule. Take your right hand, adjust it in a curling shape, and have the thumb pointing in the direction of electricity flow. The curling shape you've just made automatically points in the direction of the magnetic field lines. Now, you can tell Mr. Engineer you know of the right-hand rule. Let us modify our straight wire and shape it into this low P shape and connect the terminals accordingly. What will be the direction of electricity flow in this scenario? Correct. Electricity moves from positive to negative, hence this direction. Let's now take a deep dive and follow the electricity flowing inside this loop while also analyzing the direction of the magnetic field. Having a chip around the loop while looking at the field lines denotes this, and this results in a complete magnet with magnetic field lines moving from north to south outside the loop and south to north inside the loop. Does that ring a bell? That is how permanent magnets work. And so this denotes this as the south pole of our electromagnet and the other side as the north pole. Imaginary, just as how magnets work, but for the sake of the visualization of the video, we are going to keep them visible for the next sections. But wait, what happens when we reverse the electricity flow again? Shall we? The results speak for themselves. Not only does the electricity move in the other direction, the whole magnet changes its poles in relation to the direction of electricity. But when you de-energize this loop, the magnetism also fades away. Bonus fact though, you have just seen how electromagnets work. We can push things a little bit further for the final section of this video. Let's take our square magnet, separate it into two individual north and south poles. Let's span them across this loop with no consideration to orientation whatsoever. Watch what happens when you complete the circuit again. Now that is exactly how magnets react to each other. Like poles repel and unlike poles attract. Let's watch this closely. The south pole of our electromagnet is attracted by the permanent north pole, while being repelled by the similar south pole. The opposite is true for the north pole of our electromagnet, with the permanent north pole repelling it and the south pole attracting it at the same time. This results in torque generated at the motor's axis of motion. Let me rephrase. This results in finite torque generated at the motor's axis of motion. And I say finite because, well, let's watch through the video. The magnets can only attract or repel until they are closest or furthest respectively. This means that at some point, our motor will have no torque generated at the axis of motion. Watch this closely. The motor no longer generates torque because unlike poles are at their closest with like poles at their furthest. That's a problem, but luckily we can resolve this problem. In order to generate a force or ultimately torque, unlike poles need to be furthest from each other and like poles closest to each other. What do you think can be done to achieve this? Pause the video and comment your thoughts on the subject. We can manually swap the magnets over, but that would be very demanding. Remember when we swapped the two terminals around? That resulted in opposite poles generated around the loop. We can do that to our motor as well, making the unlike poles at their furthest and like poles at their closest. The motor starts generating torque again, but we would need to swap the wires around every half cycle to achieve rotation multiple times. We can resolve that by using something called a commutator at the ends of our coil. This reverses the electricity flow every half a turn automatically, and the brushes have springs inside to help it stay in contact with the wire. And voila, we have a motor. Here are some modifications used in every motor factory to make these work more efficiently and produce more power. We can add a bigger battery to the circuit, which results in bigger, stronger magnetic field lines, which in turn generates more torque. We can add a bigger or stronger permanent magnet, which will make the field lines around the magnets a bit stronger, which in turn generates more torque. We can wind our loop into more sections, which in turn concentrates these magnetic field lines, making them bigger and stronger, which in turn generates more torque. We can add more of these loops, taking turns and running the motor efficiently. The more we add these loops, the more powerful and smooth our motor runs. And so we end up with this, a complete motor we can employ on a day-to-day basis. You've just learned how motors work.